about prompting and chain of thought, and we got to the point where we were trying to study what makes chain of thought tick, but we didn't have quite enough time to finish, so we'll finish that. And then today we'll move into specialization, which is like a very big topic on its own. We're only really going to scratch the surface. But we'll talk a little bit about how do we fine-tune these models, how do we fine-tune them efficiently in particular, because these are huge models, so it's not really cheap to fine-tune everything. And then we'll kind of talk about how we repurpose language models especially to do other things as well. So we'll get into adaptation. And then finally, if we have time, we'll talk about what's called model editing. So one thing about these models is that they also memorize facts, right? It's not just that they know how to do stuff. They also contain a ton of information. Over time, that information will become stale, and we'll want to figure out a way to refresh it or update it. And we don't want to necessarily train the model, which is pretty expensive. We want some way to treat it like a database and edit some entry. And model editing techniques are basically trying to do that. So we'll briefly talk about those. All right, before we jump into it, logistics, not too much. Homework 1 is due on Thursday. Everybody okay with that? OK, sounds good. A bunch of folks have already submitted. We are also on Thursday going to release information about presentations. The only thing you really have to do at this stage is to form teams. So if everyone could form teams of 3 to 5, 6 folks, that'd be awesome. I'll give some examples of what papers you could pick, but you are free to pick whatever you'd like. And then we'll talk about kind of what I expect from you folks, which is just a little bit of text on why you want a paper, and then kind of what the actual process will look like. We'll also release some information soon about the project. Same deal, basically. Form teams, come talk to me, propose something you're going to do, and we'll see how we can help you out with that. Cool. Any logistical questions? None. OK. So where we're at is in this specialization section. So today we'll start talking about it. And then we'll specifically talk about alignment. Now, alignment's going to be one particular form of specialization. It's going to be more specific, and there will be kind of more concrete techniques for doing that. And then we'll talk about one very specific form of specialization, which is going to involve reinforcement learning. So that's going to be next week. We'll spend a bunch of time thinking through what that looks like. And then finally, we'll start talking about how do we do all of this stuff efficiently. Efficient training and efficient inference. Any questions on what we're covering? Oh, awesome. All right, let's jump in. Here's the outline for today. We'll talk about fine-tuning models in general. It'll turn out that it's pretty difficult. So we'll have to develop a new technique called adapters. This is going to be a technique that gives you good performance for fine-tuning, but it's also going to be relatively cheap, which is exactly what we're trying to get. So we'll talk a bunch about different ways of doing that. The most popular adaptation technique is called LoRa, so we'll spend a bit of time with it. Then we'll get into settings that are more challenging. So specifically, let's say that we want to go from one data modality to another. We'll talk about how we do that. We'll call it cross-modal adaptation. We'll talk about a couple of techniques, and finally, we'll talk about one that's very powerful called Orca, but it will require us to kind of develop some machinery first. So we'll have to talk about something called optimal transport. So we'll spend a bit of time there, and then we'll talk about this model editing piece and kind of one popular technique for it. All right, so let's start from the beginning. And I'm going to spend a few slides just on what we finished off with last time, which was chain of thought. And again, this was let's think step by step, or alternatively, in context learning, let's make sure all of our examples have worked out solutions. OK, and it wasn't completely clear to us when chain of thought was actually beneficial. And this has actually been a bunch of research, and it's pretty interesting. It turns out that, maybe not that shockingly, it's most useful in cases where there really is some kind of multiple step solution that should be there, and especially on cases where there's a lot of training data for this. So math is the most popular, and to some extent, symbolic reasoning, which is one of the examples that we saw. Here's kind of a nice plot showing what took place when people experimented with chain of thought and without it. So this plot over here is showing you the change, the delta in performance, when you include chain of thought over the reference, which is no chain of thought. And as you can see, it's not guaranteed to improve things. You're seeing the 0 line over there in the middle. There are points to the left where adding chain of thought made things worse. So there's no guarantee that for sure you're going to do better. But you see there's some changes, and they're trying to model the distribution for different categories of questions. And if you look up top, things like text classification, you're really not seeing a benefit there. But here on the bottom, things that involve logical reasoning, math, symbolic algebra, stuff like that, you do see a lot more improvement. So again, this chain of thought idea is not something that you necessarily always want to do. It kind of depends on, one, the kind of problem, and two, was the model shown enough data to really be able to go out and actually do this. And this is kind of the radar plot that we also show for different topics. As you can see, that yellow line is showing you kind of how far you can get. You do much better for math. But on the other hand, for things like common sense reasoning, knowledge, you actually don't do much better. Cool. Does this make sense for everybody? Now, granted, this was important, let's say a few years ago or last year, because you really had a choice of whether you wanted to do chain of thought or not. Today, if you're using a closed source model, usually that decision is not really there for you. The model will internally do chain of thought if it wants to, and that's not something that you can very easily control. But for open source models, you still get to make this choice, and you get to pick what you think makes more sense. All right, so let's talk a bit more about when you expect language models to do well, and when you don't expect them to do well, and what techniques are involved. So here for chain of thought, we saw, OK, for certain things, you don't really do better. There's actually lots of cases where language models will struggle. And one that you've probably seen are simple things like arithmetic. Right? So adding big numbers together is actually not that easy for language models. OK, so what's the reason for this, given that it seems like a very simple and basic thing? All right, who has an answer? Why can a second grader add 10-digit numbers correctly, reliably, and the language model not? Go for it.
Because the median corpus of adding 10-digit numbers may not necessarily include the example where these two 10-digit numbers were added together, and the language model just predicts next token.
Your answer implies that language models cannot generalize at all, right? So that's a very pessimistic take, which is reasonable. But we know they can generalize for much harder problems. So a model that can solve fairly hard competition math problems that it's never seen before still can't add 10-digit numbers. So although I agree with your answer, it's not the complete answer. All right, any other guesses? Go for it. Yeah, tokenization is a good point, right? So the truth is we're not doing mathematical operations the way you normally would, where you say, here's a number, here's a number, here's an operator, go do it. You are turning all your numbers into token sequences, your operation into a token sequence, and so forth. So things can be pretty difficult when you have to do that. And that's why language models can struggle on very basic tasks. You're really saying, hey, for numbers of any length whatsoever, you should be able to figure out how to turn them from long token sequences into things where you can actually work out some computation reliably the same every time. It's actually very non-trivial. It really is not something that you should be able to expect from these models. OK, now the good thing, though, is that we do have a calculator, right? So the simple solution to things like this is you can hook up your language model to a calculator, make it do the work there, and then just output the solution. So this is the entire area of using tools with language models. And it makes a lot more sense because our goal is not to have our language model perform neurally every single thing that we can conceive of. We've already built reliable software to solve all sorts of problems. We should just reuse that software. So now the challenge is not so much making sure my model can do all these things. It's more, can it figure out how to call the tool and how to get a good answer and how to be able to use that answer and the rest of its flow of commands, reasoning, et cetera. OK, everybody OK with this? Cool. OK, so how are we going to help it? Let's use these external tools. And let's take a quick look. I'm going to show one example. The simplest kind of tool that you really can do is essentially to write programs and then go ahead and execute those programs. You can compile them. You can use an interpreter, whatever. So here's a simple example. Let's say that we want to have our model be able to write Python tools. How do you do that? Kind of not surprisingly, it's not super, super different than what we talked about in chain of thought. So here's a fun example. This is a chain of thought case where the model actually gets it wrong. It's still a word problem, very similar to what we saw before. But in this case, even though we do have a worked out example in our context, the model's output is still incorrect. And again, the reason is this arithmetic problem, right? So sure, the model worked out some steps, but then it got a calculation wrong because it's not good at these kinds of calculations. So the solution is the thing you're seeing on the right, instead of showing a worked out solution in words, let's show a worked out solution in code. And of course, I mean, you could say, well, it's much more difficult to write code rather than writing a solution. Well, at least for some problems, it's really the same thing, right? In this case of simple grade school math problems, it's not too different, right? We actually go ahead and create instructions for all of the lines of the solution. And then at the end, we show what's supposed to happen. And then finally, we have a formula. We can print an answer. We can go ahead and execute that program. Now, notice that in this case, we didn't really require the model to do anything else, right? We didn't train it to use external tools. We just said, hey, go ahead and intersperse some Python commands inside your chain of thought solutions, and let's let the model pick up on that pattern and do it itself as well. OK, and again, what's the advantage here? It's because the model does not have to do the actual arithmetic steps anymore. The Python interpreter will take care of that part. All right, everybody OK with this idea? Now, modern language models will not necessarily require you to actually go do this. They will figure out, basically, hey, I'm supposed to write a program here, or it's more useful for me to go write a program here, and it'll actually go and do that. So even this here is no longer super necessary. And you can run some experiments to see that. Let me show you a quick example. I tried something a couple of days ago where I wanted to solve some very basic time series problem. And ChatGPT, and this is GPT-5 thinking, instead of actually trying to solve the problem directly, it said, OK, well, let's write some code. Let's do a little bit of filtering on our data. Let's run a very simple model. And let's do this forecasting problem. So this will happen automatically. Typically, it's not something that you have to worry about yourself anymore. The only time where you really want to think about these kinds of things is, you may want the model to write code that's specific to something. So it may turn out that there's some really useful C package that you want to use. The model may not be aware of that. You may want to encourage it to look up the right way of doing it. Cool. Any questions about this? Awesome. And this paper over here is actually very clever. I like this idea a lot. The missing piece basically was that models are already trained on tons of code. Just have to make sure that they're actually thinking of using it. And that wasn't always trivial. All right, so let's see some prompts for this. We said that the only thing that's different is that we included information about code. We interleaved these code and text instructions. And you can see a bunch of examples of this. These are coming from the paper that I just showed. Right, so you translate the solution to the question just into a bunch of code. Sometimes you want to add comments. Other times you want to have specific packages being loaded. But in principle, it's all basically the same thing. Cool. Any questions? Now, one thing you may think about is, well, what if my model has never seen the kind of package I want to use, or worse, the kind of programming language I want it to use? That's where you have to get into more complicated things like fine-tuning, because your model just will have no capacity to be able to create new things it's never seen before like that. All right, let me show some more example. This is called Program of Thoughts, extremely similar type of paper that came out at about the same time. You can see that it's doing roughly the same things. Right, so over there, if you're trying to do things like, try the Fibonacci number sequence, it's very difficult for the model to be able to actually add all those numbers by itself. But of course, you can write the function and recursively call it until you get the right solution. And these are really the exact kind of problems where using an external tool makes sense. Your model really does not have a place to do a ton of computations on its own. So if you ask it to do anything complicated that requires chaining together lots of little steps, it'll probably fail unless it uses these tools. All right, so let's talk about tools that are more general than this. So these are just programs. You can use anything you like. Now, the one thing that we're trying to do here is to avoid doing too much human annotation. You really want the model to figure out on its own that it's supposed to use a particular tool. There is kind of the first paper that introduced this idea. It's called tool former. Terminology, again, transformer, tool former, you get the idea. So it basically introduces API calls, and you fine-tune with some special tokens that are meant to be whatever tool should be used. And then the model can figure out on its own, once it's been fine-tuned, what to do. So here's an example. Let's suppose that I want some lookup in some database, right? I want my model to be able to do that. Now, out of the box, the model may not have that capability. It doesn't have access to any database. Then what I'll do is introduce this special QA token over there. And I'll get some training data that includes this QA token and some examples of how to use the tool that corresponds to it. And I'll fine-tune on those examples. And then that gives the model the ability to go actually look up stuff using that token that we just introduced that connects to a particular tool. But this required fine-tuning, right? The model doesn't know that QA call to begin with. You have to actually create a bunch of examples and instantiate them and fine-tune the model before you have this capability. All right, everybody okay with that? Now, are you going to use this old technique? No. In practice, there's very recent protocols that you use to standardize tool calls. So MCP, Model Context Protocol, is kind of what we'll do. We'll talk more about it later, but it gives you the ability to call any external tool you want and a systematic protocol that you follow for this. OK, so hopefully we're all convinced. Language models do a lot of things, but we don't want them to do all those things. They're not perfect at all of them. We want to be able to take advantage of external tools. How we call those external tools depends. Sometimes it's built into the model, like coding, which the model knows how to do for lots of languages. Sometimes we need to do something new and external, and we have to follow some protocol to show the model what to do with it. That's the big story so far. Everybody OK with this? Cool. OK, awesome. So let's keep going. Now, we're going to get into this adaptation part of the lecture. And you can see that we've already started talking about let's fine-tune the model to give it some new capabilities. Prompting was great because it didn't make us do any of this, right? We said we never change the model. At most, we do things like in-context learning, where we show a bunch of examples and let the model try to deal with them and do something there. But we never actually change the weights. Now, this works a lot of times, but not always. Sometimes the model has to be able to do new things. And in that case, we will have to actually train the model some more. And we'll refer to all of these cases as adaptation or specialization. And why would we need to do this? Well, the answer is that sometimes we get huge performance gains for very little by fine-tuning. Here's a plot that I actually like quite a lot. So what this is showing you basically is trying to normalize the compute cost of more examples versus fine-tuning. These are two different operations, right? Fine-tuning means I'll have to train my model, change its weights, whereas in-context learning says I'll load up the context window with more stuff, but I'm not going to actually change the model. So even though these two things are different operations that are not directly comparable, both of them actually involve some amount of compute being spent, right? When I go fine-tune, I do a bunch of backward passes to change my model. That's some number of operations. When I go ahead and load up the context window of more examples, that's all inference, but that also involves more computations. Everybody agree with that? Well, we can conveniently just go ahead and measure the number of these guys. We're going to do that in flops. Those are floating point operations. And we just measure how many of them we have. And this way, we can compare in-context learning to fine-tuning. All right, everybody agree with that? OK, so we can compare it. And we can say, hey, what buys us the most accuracy? What's the best use of our compute budget, whatever it may be? And one thing we can do is kind of look at different cases over here. And as you can see, you're not really getting too much for some of these giant models, because you're actually using up a huge number of flops. These are all with in-context learning in blue, compared to what you can buy yourself by doing few-shot learning. And here, few-shot learning is in the fine-tuning sense. Again, going back to our conversation on terminology, we're using it in different ways. But this is fine-tuning with a small number of examples takes you from that green circle to the star over there. So as you can see, we pay very little in terms of compute, but we jump way up in accuracy. Whereas using bigger models of in-context learning, not nearly as good, they reach roughly the same accuracy, but you're paying way more in flops. All right, everybody OK with this idea? Now, ignore the plot. It's not even really showing you how in-context learning scales. There are some other papers we'll talk about that do show that. It's just showing you an example how basically a small amount of fine-tuning can really be a huge benefit without too much cost. All right, so this is actually quite a nice paper. And all of these models are quite well known from a few years ago, T5, T0, and so forth. These are fairly major families of models, but they're a bit old at this stage, so you won't often use them. OK, so let's get back to kind of the very beginning of our class. We spent a lot of time talking about foundation models. And we said the basic idea of foundation models is we're going to train this generalist model first. And then later, we'll come fine-tune it for special tasks. So that was our original idea. We're just kind of getting back to it now. We spent a ton of time talking about language models and how we can use them without specifically fine-tuning. Now we'll return to this original foundation model story. Okay, so we said that the way we're going to do it is that we're going to develop our foundation model. We'll typically freeze some of its layers, maybe all of them, and then we'll build some extra stuff on top and train that extra stuff. And that's what's going to give us this new capability. So we shared this picture before. We said, hey, let's create a fake task. Let's train a model that can do this fake task very well. It did this in a self-supervised way. We never had to get any label data. In this case, we had a bunch of bird pictures, and we rotated them. The model had to learn how to unrotate them. And then from this, we said, let's put on top of this a few layers, maybe just a single layer, and we'll get some label data and train a model that sits on top of it. So this is our foundation model story. We have pre-training over here on the left, self-supervised with lots of data. And then we have fine-tuning here on the right, small amount of data, maybe a small number of layers on top of our foundation model. OK, everybody OK with this story that we started off with? Cool. So this is exactly what we're going to try to do now. Now, there are different things that we could do, right? So this is the interesting part over here. Previously, we said, hey, let's take these layers, the purple guys, and let's go ahead and freeze them when we train something on top of it. And in this case, we put a single linear layer on top of those frozen layers that we got from pre-training. This has a special name. It's called linear probing, which is not a very intuitive name. But there's nothing stopping us, really, from potentially fine-tuning some other parts of these layers as well. We don't have to stick to frozen layers with a trainable linear layer. We could also train maybe one layer back, or maybe all of these layers as well. Granted, if we don't have much data, we could have potential problems with things like overfitting. OK, everybody OK with our story so far? So notice that we're just now returning to what we talked about to begin with, our entire kind of foundation model story. We just had this detour through language models that really emerged from this entire foundation model philosophy. But for the most part, were not used in the way that we talked about. We did a bunch of things so we didn't have to fine-tune. Now let's figure out how we can actually go do that. OK, so the simplest thing that we can do is really just to go fine-tune our entire model. We start off with this pre-trained model. The weights are already determined by training on the pretext task. But we go ahead and say, let's change all of them to do some particular task for us. OK, so that might be one thing that we want to do instead of linear probing. And after all, there's some reasons for this too, right? If I use frozen representations coming from my pre-trained model, if they're not very good for the task, potentially that might lead to very limited performance. Similarly, if my one linear layer that I added on top is not good enough, really, I need something more complex, then again, I actually need some more capacity there. So what I can do is just go ahead and change all the weights. This sounds complex, but it's really not, right? It's just a one-line kind of thing. Like I go ahead, I take my pre-trained model. Here it was BERT, but it can be whatever you'd like. And I say, go ahead and train. So full fine-tuning, although it's the most complex in the sense of I'm changing everything in my model, it's also the most simple, right? It's just training your model the exact same way you would have trained it from scratch, except you have a different starting point. The starting point is your trained foundation model. All right, everybody OK with full fine-tuning? And again, the motivation here is, sure, I could do linear probing. It's simple and cheap. But linear probing might have limits to how good it's going to perform. These limits are because whatever task we're going for might be too hard for linear probing. Or maybe the distribution is too different, and I do have to change things more than that. OK, so this is full fine-tuning. Unfortunately, just like everything, there's a trade-off here. There's some downsides as well. We have to fine-tune all of the parameters. The most obvious thing is that it's expensive, right? For me to go fine-tune all my parameters, my gradients are going to have the same dimension as the full model. So if I want to do full fine-tuning on a 100 billion parameter model, once again, I'll need a lot of GPUs for being able to do this. And it's kind of out of reach for us as consumers. Really, the best we can possibly do is something very small, sub 1 billion parameters. Now, that might seem like the only issue. It turns out, though, that we'll have the other problem as well, which is that we could very easily potentially overfit. And if we overfit, then if we have anything out of distribution, we might really struggle with that. So I'll show you an example here. This is a very nice paper from Ananya Kumar. Here's what's going on. I'm going to say there's a pre-training phase that's going to go ahead and train our pre-trained foundation model. And then we have some choices for what we can do. What you're seeing here on the left is full fine-tuning. We're going to run backprop through the entire model, through all the layers, and fine-tune everything. That's this left column over here. And then we'll go ahead and evaluate the performance of the fine-tuned model in two cases. One is going to be in distribution, which means that the samples are from the same distribution as the ones we fine-tune on. And then we'll do out of distribution. Those samples are slightly different. And again, this is very normal because in real life, you'll often see samples that are OOD. So what happens is maybe not too surprising. In distribution, you do very well, 85% accuracy. But out of distribution, you struggle, right? It's below 60% here. And the reason simply is you've overfit quite a lot to those in distribution samples. The foundation model has now lost some of its generality. It is now very focused on this particular in distribution task and much worse at other things. And this is not something esoteric or unlikely. You actually see this all the time in language models as well. For example, people will fine-tune a language model to make it better on math benchmarks. If you go test that model on anything else, it'll perform way, way worse. It'll have lost the ability to do other tasks that are more general. OK, so one solution for overfitting is let's limit our model capacity. And linear probing is exactly that. It does not change any of the pre-trained features. It just says, here's one more layer. Train that one linear layer and nothing but that. OK, now, of course, not surprisingly, there's limitations on how good a linear layer is going to be. And as a result, you have slightly worse performance for in distribution compared to full fine-tuning. But you are better on out of distribution. All right, everybody OK with that? Why are we better on out of distribution? Well, it's because we haven't really changed this more general model nearly as much. It's no longer as closely tuned to this particular in distribution task. Now, this all seems like kind of a trade-off we'll have to pay, right? Either we're better at the task of interest for fine-tuning and worse at everything else, or vice versa. Now, the one thing that's very nice about this paper is that it says, look, there may not really be that trade-off. You should just do things slightly differently. And this is something quite interesting. What they end up doing here is that they do linear probing first. They use the result of linear probing as an initialization, and then they do full fine-tuning. So this is something very intriguing. It's basically saying, hey, instead of messing with lower level features right away to be able to get good at the tasks that we're currently fine-tuning on, let's do something different. Let's put linear probing. Let's get something decent going for an initial model. And if we have to do some small shifts of all the lower level features in addition, that's OK. We can do that. But we don't have to change everything right off the bat. So kind of a two-phase process that gives you the best of both worlds. And of course, you don't always do better in both of these categories. But at least sometimes you can, which is something quite nice. All right, any questions about this? Anybody confused by what I mean by this two-stage thing? Cool. Just repeating it one more time, all we're really saying is this was bad because a lot of the lower level features, lower in the layers, were changed immediately for a particular task. And we don't have to do that. This is bad because we never change those guys. We sometimes have to do that. This gives you best of both worlds. You find a good solution that's close to the optimum, and then you slightly change all those lower level features in a way that doesn't break everything for other tasks. Cool. OK, so very nice paper. I encourage everyone to take a look at it. Now, so far, we've been talking entirely about full fine-tuning versus freezing and adding one layer. Of course, there's additional options for what we can do as well. There's partial fine-tuning, which is very natural. You can just fine-tune some layers instead of all of them. Here's a quick example, although this paper is doing something slightly different. I can say, hey, let's lock some of my layers and unlock some other ones. And what I'll do is just fine-tune the choice of layers I want. Now, traditionally, I will say things like, let's go ahead and unlock the top layers and not any of the bottom layers. And I'll decide how many of them to do, depending on how much compute I have, how much I'm overfitting, things like that. But you don't even have to do that. You can actually have the bottom layers sometimes be trained a little bit, then the top layers, and so forth. So really, you can create a whole schedule of which layers to unfreeze, which ones to freeze. And you can kind of control how much compute you spend as a result of this. OK, other examples. We already talked about this one. We were talking about soft prompting. Just as a reminder, that meant that we have some tokens that are no longer language-based. They are just continuous parameters, and we tune those guys. That in itself is also a form of fine-tuning. Now notice it's a little bit different, right? Because we're not fine-tuning the weights of the model. We're fine-tuning some extra weights that we consider to be tokens. But in practice, these are weights that influence the model as well. So even though we've kind of added them in, still no different, right? We're still fine-tuning over here. OK, so this was a story there. We said, hey, for different tasks, let's go ahead and train different prefix tokens. They're prefixes because they go at the beginning of my token sequence for my input. And how do we fine-tune them? Well, we get a bunch of data for each task we're interested in. We go ahead and initialize these continuous tokens, and then we fine-tune them to perform well on that particular task. And the thing that's especially nice about doing this is notice that since I'm not touching any of the model weights, I can easily switch to a new task by swapping in some new pre-trained prefix tokens. So let's say that I wanted to do, for example, table to text over here, which is one possible task. I can go ahead and put in these tokens. But let's say I want to switch to summarization later. I don't have to get an entirely new model. I can just put in these tokens that I've pre-trained. So you kind of have these, and I shouldn't use this term, but yeah, you have these kind of like cartridges. You just plug them in for the task that you want to use. The rest of the model, all of the weights, they don't change at all. Everybody see what I mean by that? So this is very good. That's another annoying thing about full fine-tuning. I've changed all the weights. If I want to switch to a new task, I have to go ahead, start the base model all over again, tune all those weights again, use that model, and so forth. And if I want to keep fine-tune models for a bunch of different tasks, well, I'll have to pay the memory cost of the full model for all of them. And that's pretty annoying. Whereas for prefix tuning, I only have to do that with these prefixes I've trained. There's only one copy of the model that sits there otherwise. So this is something that's very nice. And this is just one example of a more general family of techniques that are called parameter-efficient fine-tuning, PEFT. We'll talk a bit more about these. Go for it.
So with the prefixes, are they, like as the name suggests, put like right at the start of the?
Yes.
OK, gotcha.
But not because that's like strictly required or something, but yeah.
But is it like, how do you specifically kind of like connect them into the model properly if each one has like each prefix is trained differently? So if like the transponder isn't changing, then how is it that they connect? Is it the same way with each prefix, or is it different?
So each of the prefixes are per task. The prefix is a fixed length vector. It fits into the model because they're the same dimensionality as a language token would have been. I say, hey, let's get a bunch of data, right, which has whatever I want it to do. So again, this is supervised data over here. If I'm doing table to text, I have a bunch of pairs, tables and the corresponding answers. I go ahead and fine-tune on those data sets, but I'm not fine-tuning my model weights. I'm only fine-tuning these prefixes, right? That's it. Then I keep them for later. When it's inference time, whatever task I have, I plug in the prefix and I run it. Yeah.
Is non-text inversion a type of prefix tuning?
In a very general sense, yes. Okay. But not that I know anybody doing it that way. But I see your point, yes. Yes, we'll talk about that later. That's a very open area of research that we don't really perfectly know how to do currently.
Okay.
Which is better, like prefix tuning or linear programming? Do we have like?
It depends, is the answer. It's a per task kind of question. There is no general answer. I will say this, right? If you want to do linear probing, you really need a very simple task that's entirely dependent on features and nothing but that. If you want anything more complex, you have to do some type of fine-tuning. And it's going to be one of these PEFT techniques that we'll talk about in a second. So that's typically what you'll do. Right. Yeah?
Is the prefix part the part of the model, or is something that you added to?
You really add it to the model. But I mean, it's always there, right? Okay. We're talking about input tokens. You just say, hey, keep some of my input tokens that I always put in, make these things trainable, and inject them. But technically, it's not a model weight itself, right? Cool. All right, so we're getting into this idea of, hey, it's expensive to change the weights of my model, and it's annoying and challenging to figure out how to pick some of them so I don't have to fine-tune the whole thing. Maybe the solution is let's fine-tune other stuff that's not already in our model, And this idea of prefixes is just one example of that. We're going to talk about other cases as well, but this is a whole area called parameter efficient fine-tuning. And again, the logic here is if I want to fine-tune a model with billions or trillions of parameters, that's too expensive. We want to be able to fine-tune fewer of those parameters. So let's go ahead and be parameter efficient. Okay, so that's what we said. Look, these methods that we talked about were not so good so far. We had to figure out which layers to train. We had to figure out how to deal with prompts, like for prefix tuning. We had all of these choices that were difficult to make. Let's go ahead and kind of figure out something else, right? And that something else is going to be kind of what's going to happen in this plot. We're going to systematically add little modules with extra parameters, and it's going to be those guys that we fine-tune. Now, this was kind of already happening in our prefixes, but we're actually going to now inject these guys into the model itself. So instead of saying, hey, our model, we're never going to touch it, its weights are what they are, we are now going to say, hey, take this connection somewhere inside one of my layers. Let's add a module there. So instead of saying, hey, the data flows upwards, we say, hey, the data flows into this new module and out of it. And inside this module, we'll put trainable weights. And those are going to be the weights that we train. And we get to control how many of them there are. We can make it a small number of weights if that's what we want. OK, so that's going to be the intuition. Now, nobody would care if this didn't work. But the very interesting thing is exactly what you're seeing in this plot over here. We're counting the number of weights. That's what you're seeing here on the x-axis. And then we're looking at how good we can do in terms of performance gains. That's what you're seeing on the y-axis. Now notice that these performance gains really are negative here. This is a comparison to full fine-tuning. So our real goal here is to be somewhere on the left, use very few parameters, while being very high on the y-axis, ideally at 0. What would be the ideal technique? It's one where we fine-tune 5 weights and have no loss, so we're at 0. Everybody agree with that? Now that's of course impossible, but you're seeing something nice here, which is that if you use these adapters, you can have next to no performance loss, all the way down to something like 10,000 weights here. Whereas if you were to do, let's fine-tune some number of layers from the top, you actually have a lot of losses as you pick fewer and fewer layers to train on. OK, does this picture make sense? So this is really the motivation for this entire field of adapters. You really can get by with very few weights and still have the same benefits as full fine-tuning. And this is great, right? Because now we can go ahead and have much less compute. And because these adapters are these modules, we can swap them in for new tasks. Same exact story as the prefix tuning. We can say, hey, I've trained adapters for task A. I can remove them from my model, swap in the ones for task B if I want to go ahead with task B. And these things are small, so I can keep a bunch of them in memory somewhere. Cool. All right, so let's see different adapters. What do we want? Again, good performance in terms of accuracy and as few parameters as we can have. Here's kind of the classical version of it. What you're seeing is just a very standard transformer model here on the left. But we've added 2 things, which you cannot really see in the color. But you can see these adapters between the feed-forward layer and layer norm. That's that yellow box over here. There's 2 locations for it. And this thing on the right is just kind of zooming in and showing you what's sitting inside that yellow box. And again, what we really want here is to make sure that we have few parameters. So one thing that's going to be important is to take our vector that's coming in, project it down to a small dimension, operate on that small dimension, which has fewer parameters, and then go ahead and up project back. So this is how we're going to control how many total parameters we have to use. All right, everybody OK with this? Go for it.
So once you want to move this to inference time and basically ship your model, how does this tend to affect the performance of the model's ability, just to process incoming information?
What are you trying to do? For inference time, are we talking about the task that we fine-tune for, or a different task?
Yeah, I'm not necessarily focusing on accuracy performance. I'm talking about just physical performance. Does the actual impact of physical performance tend to have a profound effect?
Not really. It's pretty good in general. I mean, there are currently discussions about whether, for very specific kinds of tasks, is it possible to use adapters in a reasonable way? there's a whole conversation about whether for reasoning you can really do it or not. The general consensus is increasingly yes, this does not hurt you in any meaningful way. Cool. So this is something that's actually not super new. As you can see, it's from 2019. This was way back before large language models really were a thing for the most part. Now, this actually works quite well. I'm going to show an example that actually gives you even more direct control over how many parameters we're going to get to use. And it's going to be called LoRa. This is really the most popular form of parameter-efficient fine-tuning. And very likely, if you're going to go ahead and fine-tune your own language model at home, you will most likely use some variant of LoRa. Probably you'll use LoRa with some additional tricks, such as quantization, that make it even cheaper for you. And there's a bunch of variants of LoRa that let you do that. OK, so this is the most popular thing. It's going to be actually extremely simple. Instead of doing what we did before, which is injecting a new module inside the flow, what we're going to do now is just add something to weights. Fundamentally not too different, but we're not adding a separate module anymore. The picture is going to look like the following. Sorry about that. Here is going to be one of our weight matrices in blue. That's already in our model. It's already trained. So that's already there. Now, normally, we would have added something on top of that blue guy, a separate module, and trained that separate module. Now, instead of saying, hey, put something further up, we're actually going to add new stuff to this pre-trained weight matrix itself. And it's that new stuff that we add to it that we're actually going to go ahead and train. Now, one problem is that if we decide, hey, let's go ahead and add a whole new matrix to our previous weight matrix, well, the number of weights will be the same, right? So we would get no benefit in terms of efficiency. So what we want to do is to add in something that conforms in terms of dimensions, but has fewer parameters. And specifically, to do that, we'll have to use a low-rank matrix. Right? A low-rank matrix can have the same size as a full-rank matrix, but it has fewer degrees of freedom. Everybody agree with that? And that's exactly what's going on here, which is these orange boxes that you're seeing. These are low-rank matrices that are being multiplied together to get a matrix that conforms to the size of this blue weight matrix that's already there. But because they're low rank, they have fewer parameters. And in fact, we can control how many parameters there are. That is just a rank hyperparameter. The smallest we could do is rank 1. Of course, if we're doing very small rank, we have very few parameters. Eventually, we could hurt our performance as well. OK, there's a couple more tricks. One question that we sometimes ask ourselves is, how do we initialize these pieces? And there's some tricks that help you kind of learn something useful there. And one way basically is to initialize things in one of these two components that get multiplied to be Gaussians, while the others are 0. This is more of an empirical trick that people have found trains well. It's not super, super critical. But everybody agree with what we're saying here? We've taken this adapter concept that had separate modules that got inserted into the model. We're now saying, no, don't insert them, just add them. And you can control how parameter efficient you are through the rank that you're adding it. OK, now, why should this really work at all? It seems a little bit bizarre, right? I mean, after all, this blue matrix could be some very rich thing itself. And in fact, this thing, if it's very general, just adding some low-rank term to it may not change it very much, right? And if it can't change it very much, then we might ask, well, how do you know that you can actually go ahead and become specialized to your task? So the intuition is that even when you go train a neural network without any conditions on what should happen to the weight matrices, they might really have some structure anyway. And if that structure is low rank, then adding another low rank term can really dramatically change it. And therefore, it makes sense to try to have this kind of constraint that we really develop for efficiency rather than for any other reason. Now, is this completely true in practice? Sometimes. But the intuition at least makes some sense for this idea. OK, now, where should you place these LoRa terms, right? Because I can add them to any weight matrix. They initially were applied to the attention layers, but you can really put them everywhere, and people do that. And in general, these things work surprisingly well. Now, do you have to do this for every layer? Not necessarily that either, right? So you can pick and choose layers as well. That costs you something, because you have to figure out what layers make sense. But it's not super challenging, because it's fairly easy to do this. All right, so that's LoRa. Just literally low-rank adapters that get added in and are parameter efficient because they are low rank. And this is by far the most popular thing that you'll get to do when you do fine-tuning. Cool. We are actually halfway through class, so let's take a break here, and I can answer more questions. And then next, we'll start talking about cross-modal. Let me do these.
The assumption that the
That's the intuition, right? I mean, it's not like a requirement. Let's suppose that you're not really you still do this process and see if it works. You're not going to personally like test that out. Right? It's also not a certainty, right? So you look at a situation where you're close to something much bigger. So rank is really how many non-zero eigenvalues you have in your matrix, right? So you can imagine a case where I have three, big, large magnitude eigenvalues and a bunch of eigenvalues. That would still see high rate, very close to the low rate. That technique will work very well. The other thing is much deeper. There's a concept called effective rank that kind of measures rank without saying, oh, it's all the number of non-zeros. It measures how close you are to the actual space of low rank matrices. That's sort of the efficient rule of thumb. As long as your weight matrices below effective rank, LoRa should generally work.
No, sorry.
assumptions are kind of valid. Maybe it makes sense that you just go with the
Smaller ones. Maybe. It's actually very difficult to project down to like a close matrix, stuff like that. You really actually do want to have this extra dimensionality. It's like a large space, so you don't know what's supposed to go on. These things are now manifolds, and it's not that easy to map those manifolds to something else smaller. Okay, I think we should have a long conversation on this. So the idea for a manifold is that it has like two kinds of spaces. One is called this ambient space where they live. And then there's sort of like the actual space where you can. So think of like a sphere. Two-dimensional surface is a three-dimensional space, right? So you might say, okay, well, why should I work with objects of a sphere when it's two-dimensional instead of working with a plane, for example, which is a two-dimensional object, right? And the answer is it's not always easy to go in between these things. You may just want to work on the sphere directly rather than saying, hey, work with this lower dimension. Same idea with these matrices. They're living inside this, matrix manifold or the but it's not always easy to just go ahead and map them down to some, dense space where you can do whatever you want. But there's research on this, so we should literally I have my weight matrix, I add another matrix to it. The other matrix contains the trainable context. Now how do I get this other matrix? Well, I do something like A and B trainable. And A and B are smaller. They're horizontal matrices rather than square matrices. A and B contain square matrices. Yes. Well, which is small. It's materializing the full matrix.
Yeah, I think probably the best way is just to look at
Well, you're just doing I2, right? So that's possible. Yeah. Zero shot is good, so I don't have to see the issue with that process.
Actually do that.
Yes, that's true. If you're good at prompt engineering, you will do that, right? If I have supervised training data that I can use for go out and fine tune I can do that. And they're not always even like you can choose, right? Yeah. Okay, I cannot do street distributing on closed source models, for example. I don't have access to ratings, right?
I just use one of my supervised to
Yeah. Because you have to actually have everything flow through. Like back down to the previous. That's unfortunately requires you to compute a lot. You have to backdrop through it. So. Yes. That's true for fine tuning as well. If I want to fine tune a particular layer, I have to backdrop through it to at least that layer.
But like for
You could, I mean, nothing I said here is absolute, right? Because there are methods of optimization to create this even for so there's something called zero of organization that doesn't require you to have a grade. But it's hard, right? So everything can be done in the way to it's just creative.
Oh, yeah.
I'm sorry, I don't know what's next. Go for it.
Yes. Maybe. Problem solver, right?
Not necessarily. Okay. For example, there are people who tell you how to solve a very hard math problem, but are really, really bad at actually doing using algorithms. You can come to this like for sure, right? That's really what we're talking about here. The model can figure out a high-level solution and tell you a bunch of this is what you're supposed to do, and it's right. But here's what steps results. Language that makes it super difficult. And as soon as you say, hey, I don't really need to solve everything correctly at a low level through language, suddenly things work. And that's this whole tool. Yeah, but you can put this guy in here, right? Nothing really stopping you from adding this more any weight matrix that you like. I did that. That's not a problem. I think that's annoying in general. So we need more of what we want, those guys for attention, but also your NLP layers. You still have weight matrices, right? Just the before layers. But all of those. Wherever you want, basically. Well, okay, so I don't know how you go samples or maybe there's depending on what base model you're using. Because you can do stable diffusion with whatever kind of image generation model you want, right? There's nothing stopping it. There's different choices. But yes, anywhere where you have a weight matrix, automatically try to do that. That's a question I actually have to think about the way that we do Laura plus diffusion models. Okay, maybe we'll talk about that later. Because I actually don't know the exact details off the top of my head. Yeah, that's the one.
No. I'm saying in the sense of like project related.
Yeah, yes, we're doing it basically in two steps, right? This is once I added this additional layer on top, right? That's kind of just choosing a combination of features. The other is, lower level features. Now, if I go over here, I don't control these two things separately. I have no direct control over it. I'm making steps that change all the way. So there's nothing that says, hey, you're allowed to change the top guys as much as you want, but you should not change the bottom guys too much. Intuitively, that's what we want, right? The top part, I don't care. I can change as much as I like. I get that. Right? Bottom guys, I don't want to change too much because otherwise I'll forget like the general stuff in my bottom. But this stuff here doesn't do anything. Right? Do what you will. What we're getting is we're saying, okay, well, first let's go ahead and get top guy as much as we want. It'll get us to this station here. And now we're in the shape, right? We're not that far from the and we need to change the bottom so much to go from this 83 to 85. And therefore I will. So the control is really just directly phase one, go ahead and do the top guy. Then take that initialized guy, and now you change the bottom guy. So that's where you're getting control. It's not like you're not saying, I'm not allowed to change the weights too much. It's just a false start. For all of these there specified. Now, what you're describing is what's called routing. So routing is when on the fly, the model makes a determination of, oh, let me pick out which submodels to use. Now, these submodels, they can be full trained languages, or they can be things like strong-based, fine-tuned. But only recently, and it's actually kind of annoying because you don't have to control right? It will route, but you don't really know. Whereas if you're using your own open source model, it's totally up to you. There's no routing layer involved. And the whole structure for what you can do. They give you one solve that. I actually don't know if GPT-5 has fine-tuning. You probably know better than me, but one day let you find well, suppose that I'm showing it like instead of the exact bird species that's fine-tuned on this, right? Well, the distribution shift here is not necessarily like we're changing like the actual thing of birds will look different than the birds the actual class that I'm predicting, which is a couple of things where the actually, you know, for the kind of like for yourself, you should check to see what the exact example is for the numbers. It's not very exciting. Let's see how general this is. I mean, of course, if you're already using it,
It's a lot of things, which you already know.
all right, that was a lot of good questions. I encourage everyone to keep asking questions. Even if we use up more time, I think it's worth it. Let's start by talking about a different kind of adaptation than what we've seen so far. So far, pretty much everything was adapting kind of a model that was built for data modality A to another task still for that data modality. Right? We didn't really talk about changing our language model to be able to handle non-text. Everybody agree? So we'll have to briefly kind of discuss what we could do in these instances. And again, this is an area of research that's pretty open. There's lots of fun ways of doing things. Let me at least briefly talk about a few things. So here we talked about language models, and now we want to do things that are not language. Of course, we can train a new model, but that's pretty expensive. What we're going to do instead is just adapt our model to handle this new modality. And of course, since we're changing data types, it's not going to be trivial. And another problem is that we don't really always know what kind of data modalities are really compatible with a model, even if we go ahead and adapt. So people started a while ago just trying different things for this. So this one's called FPT. They're just frozen pre-trained transformers. And the basic idea and the intuition for what's going on here is, if you think about what's happening inside one of these big transformer models, yeah, sure, they were trained on text, but at least inside the model, inside these layers, what's going on is a bit more abstract than that. That was our whole conversation about the latent space, right? We're trying to get away from the low-level details of a data modality. We're trying to look at more general stuff, more abstract things that are happening inside the model. So if that hypothesis is true, then really we should be able to kind of ignore the language-specific stuff that's happening in a model, like the word embeddings, just kind of plug in other things, but all of the internals of the model, since they're doing abstract operations, they should really work for other data modalities as well. In other words, what we're trying to think about here, what we're coming up with is saying, hey, after a layer or two, what kind of data we put in doesn't matter. There are just all kind of different forms or representations, but really there's something deeper going on that we can get from any modality at all. All right, so let's see if we can do this. Let's change the input and output layers. And we go ahead and just make some tiny other modifications like layer norm, but freeze everything else. So here's what we're seeing. Everything inside this shaded box is the full model, and we don't change any of it. But we will change the input embeddings, and of course, we'll change stuff at the output layer. OK, we're doing these changes because, again, instead of operating on language, we're going to operate on other things. Instead of outputting language, we're going to output whatever else we want. And this could be as simple as just a basic prediction. So this actually works surprisingly OK. In fact, it's shocking that it works at all. But it's far from perfect, right? So if you take this guy and you train a bunch of embeddings and try to say, hey, let's do image classification with my model, and instead of having a language generation model, it's reasonable. What we're going to talk about is a slightly improved version of this idea that actually performs incredibly well on a huge number of tasks. It has one more trick, but it will take us a little bit of time to develop how to build up that trick. OK, so this thing is called Orca. Again, it's a very general cross-modal adaptation techniques for models. It's going to get rid of a performance bottleneck that we saw in FBTs, and it's quite powerful. It's going to have a three-step kind of process. Two of the steps are actually pretty simple, but there'll be one more interesting step in the middle over here. But let's go ahead and kind of figure out what all the details are before we get too far into it. So what you're seeing here on the left is basically all that we have access to start with. So we have our pre-trained transformer, right? And that pre-trained transformer comes with two things. One is an embedder. Probably it's for text. So that's your FS over here. S is the source. It's the original data modality that we worked on and the original model pertaining to it. We are going to modify everything into a target. We'll use superscript T for the target kind of stuff. OK, so we have these two boxes that you're seeing over there. They're source embedder. So think of word embeddings. And again, we have the model body, right? That was the thing that we don't want to change, previously at least. We're calling that guy G. OK, now we want to adapt our model to some new data modality and setting. So we're going to have a target data set, just a bunch of input-output pairs, as in supervised learning, XT, YT pairs. X is the input, Y is the output. And these guys could be anything. What you're seeing over there are like protein strings and predictions of whether those protein strings are harmful or not. The bio people can tell me what that means, but anyway. We also have some source data here, which is what our original model was trained on, let's say. OK, everybody OK with this? Cool. So let's figure out how we're going to go ahead and do this adaptation process. And again, we'll only have 3 steps, and they'll be pretty simple. But the middle step will take us some work. Well, the first one is we're going to have to figure out how to put in this new data modality and how to output whatever kind of data that we want at the output. So for example, over here, my XT, which is my target data input, it's going to have to get an embedder that's compatible with the body of my model. That's my frozen pre-trained model. So I'm going to have this FT over here. This is just the embedder. It's going to replace FS. I had a source embedder. Now I'm going to have a target embedder. It's going to be for my new data modality. That's why it has this T. And this block here is green because this is something I'm allowed to train. These are trainable parameters that are sitting inside this embedder. OK, so this is going to help my input be compatible. I can plug it in to my model. I also need to change the output so that it produces what I want. For that, we'll have this thing called HT. This is for whatever target task I have. It's going to be the predictor. So if I'm predicting something with binary classification, it's just going to be some layers that are outputting a binary classification. OK, this is not very different from linear probing, for example, right? It's exactly what we did over there as well. It's just that we weren't really doing it in the context of cross-modal. OK, everybody fine with step 1 over here? We were doing step 1 really already for that previous idea of the frozen pre-trained model. OK, now step 2 is going to be the interesting step. And step 2 is going to take some machinery that we'll talk through, and probably we'll have to finish up next time. But let's just talk about the intuition before we do anything else. Now, one problem basically is that even with these new embeddings that we have, these FT and HT over here, well, what are they really doing? They're just making my new data compatible with my model. But one thing that could happen really is that it might accidentally push all of my data, its embeddings, into some part of the embedding space that is sort of not really good for my model. I can put anything, any kind of compatible embedding, into my pre-trained model, certainly, but it hasn't seen the entire space of embeddings. It doesn't know how to do a super good job with anything in the entire space. It's seen embeddings that are based on the distribution of the pre-training data that it saw. So in other words, there is some distribution over those embeddings that it's comfortable with, and not anything might be from that distribution, or it might be rare. And for that reason, I may want to do some notion of alignment of distributions. And what this is really saying is something like, hey, let's make sure that the actual embeddings I'm operating with for my new data modality are often in a part of the space the model knows what to do with. And in fact, the distribution should ideally be as similar as possible. Again, we're really talking about this idea of we're mapping into some abstract space, and we want the model to understand these abstractions just the way it did for language or whatever it originally had. So this is something that we'll have to learn how to do. We have a fixed distribution over the source data already. We're going to have to figure out how to make sure that our distribution over this new data, the target data, those embeddings, looks similar to these guys. And just to make the story a little more complex, I'm actually going to make the distributional alignment happen over pairs. So it's going to be input and output pairs rather than just the inputs. And again, by inputs here, I don't mean the raw data, the XS and XT. I mean the embeddings. So in other words, just to summarize, what I'd like to do in the second stage is to say that ft of xt, comma yt, the distribution over those guys, is as similar as possible to the distribution of fs of xs, comma ys. Okay, a lot of words. Does everyone see what I mean? Go for it.
Does the distribution match for all parameters of the embedding space, or does it only focus on sort of like the variance parameters?
No, it's for everything, right? So let's think of what these objects are, right? ft of xt is an embedding, right? It's some fixed dimensional vector. And then yt is something. We'll talk about how we deal with that something, some object, right? It could be a class. So I have this pair of a fixed dimensional vector and a class, let's say. And I have that for the source, and I have that for the target. I have distributions over these objects, source and target. I want to make those look similar. That's pretty much it. All right, everybody agree with that idea? I have distributions over embeddings, comma, the actual outputs for the source, for the target. I want to make those two distributions similar. Now, one of them, the source embeddings, I don't control them. The source outputs, I don't control them. That entire distribution is therefore fixed. I cannot do anything with it. It's whatever came out of pre-training for the model. The only thing I actually get to control is really just this ft, this embedder block. So I want to tune this embedder block for my target to make sure this distribution is as similar to the old one as possible. Because that's what my language model knows how to deal with. OK, that was complicated, but we'll get into the details in just a bit. Is anybody confused by the intuition or the idea overall? Yeah?
But the idea is to choose the input layers, and the step 2, distribution alignment, is kind of neutralizing it.
Yes. I can just swap in a new input layer, but that input layer may map a lot of my inputs to a part of the space that my frozen model has no idea what to do with. And I'm going to solve that problem by saying, let's tune my input layer so that the distribution over its outputs is similar to the old distribution of our outputs, which my model understands. Cool, good question. Other questions about this? And you can see that we're going to have to use some tools from distributional alignment to do this process. I know that I want to tune ft over here to be aligned, but so far we don't have a notion of alignment at target, right? We don't know what the actual objective should be that I will go ahead and fine-tune ft against. OK, now after we do this, we can do whatever we want. Maybe we'll fine-tune all the weights, maybe not. Whatever we want to do over here, just basic fine-tuning. It's really going to be the second step that's going to be particularly interesting. And we have 5 minutes, so we can get into it. OK, so stage 1 is exactly what we talked about. There's nothing super special over here, right? All that we're saying is we should put in these blocks. These two new blocks are for the input and for the output. What do they require? Will have to be compatible with the model. So I have to be able to take my new kind of data, xt, some new data modality. I have to be able to map it into some fixed dimensional vector that my model can understand. And similarly, I have to have an HT, an output block, that produces from the model outputs whatever prediction I want to have. So nothing special, they're just custom input and output embedders. And there's lots of examples you can think of. Let's say I want to do images, I could do some convolutional layers. They're going to transform my image into a vector that I can go ahead and push into my language model, let's say. And similarly, for the output example, I could do something like average pooling if I have a sequence, and I can go ahead and do linear layer, just like we always do. And from that, I can make a prediction, let's say classification. So this is stuff that we already know how to deal with. There's nothing really new over here. Now, the more fun part is the second stage. Again, this is this idea of doing distributional alignment. And our intuition that we said is, hey, we want to make sure that our target features, once they're in the model, are very similar to these source features. And that way, we're not misaligned. My model really understands this new data that I'm plugging in. So what do I need here? Well, to get more concrete, I want to get a function, ft, that makes the distance between distributions over these pairs small. So I have distributions of ft and yt and fs and ys. Let's figure out a way to make sure that that distributional distance is as small as we can. Now for that, not surprisingly, we have to figure out what we mean by distributional distances. All right, what is a distance between a pair of distributions? OK, what's a thing you know about, but it's not really a distance? You use it as a regularizer all the time, among other things. All right, when you're trying to match two distributions, what do you think of looking at? Oh, go for it.
Just off the top of my head, we do standard normal scaling.
Need something more complex than that that works for general distributions.
Scale divergence.
Yes, right. That's your typical thing that you think about. Now, one problem with scale divergence is that it's not really a distance. It's not symmetric, right? Like the divergence between P and Q is not that between Q and P. It also has some other annoying limitations. Your support has to be identical, otherwise you can't do it. We're going to need some other tools here. But if you guys have seen things like total variational distance, stuff like that, it's pretty standard. OK, so let's see what the right one is. We are actually going to build one. It's going to be called the optimal transport dataset distance. There really are a million things that we can use here. This is just going to be one that's especially useful for this scenario. And it's going to be computationally tractable. Because computing distances between distributions is not that trivial. You're talking about what can often be a fairly complex operation. OK, I'll skip the picture for a second. But let's start talking about what optimal transport is just for a second. OK, so since we're going to be talking about a distance, one thing we can ask ourselves is, how do we measure how far we are? And one possible answer to that is to say, well, if I want to take my starting point, transform it to my endpoint, and I want to figure out the shortest way of doing that, that's one easy way of defining distance, right? How far is where I'm standing from over there? I could walk to over there in the shortest route and count how many steps I take. OK, everybody OK with this way of defining a distance? OK, and that's exactly what we'll do here. Now, our distances are not physical distances. They're distances between distributions. But we can play the same game. We can say, hey, the distance between distribution A and B is the simplest or shortest way to transform A into B. Everybody agree with that? Now, how do I change a distribution into another distribution? Well, I change the probability mass on all of the items in the support of the first distribution until it looks like the second distribution. I can do that in many ways. We're going to look for the way that's the shortest, the way that requires the least movement, or more generally, the least cost. OK, everybody OK with the high-level picture here? OK, well, the math is going to look slightly hairy initially, although it's actually not super complicated. What we're going to do is the following. What we have here are two distributions. That's the mu and nu over there. And we're going to try to turn mu into the other one. OK, and to do that, we're going to say, hey, let's take little pieces from each of the parts of the support of mu and transform them to go sit somewhere else. Now, what this ends up looking like is basically just a joint distribution. That's really what a joint distribution does, right? It says, OK, I have two marginals, and I see how they interact with each other. And it literally tells you, yeah, I can transform the first distribution into the second one by just saying, hey, how many parts of each of my items for one go into the other? And by doing that, I can go ahead and transform one distribution into another. But the bigger question is, well, how much cost do I pay for it? Which is that question of, well, how far did I walk to go from here to there? And we're getting that through this cost function, the C of xy. If I'm taking a distribution over x and moving it into pieces over y, I might pay some cost. That can be general. And then how often that happens is just computing the actual kind of joint distribution there overall. So this is what we have here. It's a very simple formula that tells you essentially how far do I have to go walk? What is the overall cost of changing one distribution into another? And really, we can visualize it in a fairly easy way. All I'm really saying here is something like the following. Suppose I want to take that top guy and shift it into the bottom guy. Well, as you can see, there's more of a valley in the lower piece, right? I have to take some stuff from the top, move it out of there to create this valley. Now, I can change anything I like, but how can I do it while moving the least stuff? That's all that we're really saying here. This is just a fancy formula for doing that. Go for it.
Isn't this just velocity distance?
We'll get to it in a second, but yes.
I just didn't know.
All right, so this is going to be the way that we're going to talk about how to compute a distance between a pair of distributions in a way that costs us as little as possible. In other words, that requires the least distance moved. And we're going to talk about how we transform this expression into something that we can compute for this problem of aligning the distributions for our cross-modal case. But we're out of time, so let's keep talking about this on Thursday.